Can you just give this insight starting from the creating table, inserting data, and till the, I think, yeah, you are covering these things, but I just want to understand how the disk level it is storing, and whenever we are writing query, give that complete picture.
Yes, we'll be seeing that. Yeah. So all these components, right? The cylinders, master index, cylinder index.
Yeah.
So all this will come into picture when we store retrieve the data. So we'll be seeing about that one.
Okay.
Okay. So the first one is about the cylinders. Okay. So each amp, as we know, is attached to a virtual disk, which in turn has the physical disk drives, right? So this is where the amp stores their table and an overall picture. Correct?
Okay.
So each amp disk is made up of thousands of cylinders. As we know, the disk is made up of cylinders, right? So inside the cylinders are where the data blocks are stored. And inside the data blocks are where the rows are stored. Okay, so the physical drive and then the cylinders, inside the cylinders, the data blocks, inside the data blocks, the data rows are stored. Okay, so this is the overall picture. So when an AMP wants to retrieve a data from a particular table, right? So what this parsing engine will do, it will convert the table name to a table ID. Okay, so basically it will parse the table ID, hash the ID, and then it will get a table ID. Okay, and then the AMP then uses the master index. So there is an index called master index. The AMP uses that master index like a phone book to look which cylinder the data blocks are stored. Okay, for this table. And then AMP uses the cylinder index to find which exact block this row resides. So basically the table name is hashed into table ID, and it will look for the
sorry, I'm just interrupting you. Okay, so here you're saying like AMP is consisting of thousands of cylinders. Okay, so it's something like cylinder means, or we are calling disk. So it's going to write horizontally or vertically. So I was having the doubt. Just for my curiosity, I'm asking this question. Okay. It's if we imagine like a kind of a pipe or something, that's a real kind of an object. We can call it as a cylinder. When it is writing on for the disk, for the cylinder, that peripherence is at a horizontal level, it will write that way, or how exactly?
So basically how the disk works is, right? So when you zoom in the disk, right? So maybe I will try to put a picture in next session. So
something like says like a CD. Okay, wow,
yeah, consider the CD exactly. Yeah, so
CD. Okay, what I'm just giving example. There is CD-ROM. If you get some 550 or 100, like that, you have some box. So in that one, that cylinder is cylinder means that center thing that is holding those circular kind of things. They are revolving.
Right.
On top of that, it is writing in such a way, or how exactly the mechanism?
Right, exactly the same. Physical world, like how a CD works, is same as the disk, right? Okay. So basically, if you see, the CDs are again consists of these cylinders, tracks, we will call it as. Okay. So in that tracks, the numeric data will be written, like zeros and ones combination will be written. So when the needle is reading, right, so it will be over it writes from the center and then it goes until the end with the
Okay.
oval circular motion. So when the
Okay.
data is read, right? So what the needle will do, it will just uh, go to that particular track. Okay, so each track will have a continuity. Like once this track is done, the next continuity is in this track. So the previous
Okay.
track will contain the data. So
Okay. That means first it will do the inner circle. After that,
right,
outer
correct, correct.
circle. Okay. Like that, it will do circle by circle. No
Yes,
writing.
yes. It will do circle by
Okay.
circle. Yeah. Because the
Okay.
disk will be rotating and the
Yeah.
pointer is
If you
movable.
see, some CD is written, we can see something like if it is half written or
Correct,
some percentage written, we can see that space that is something
correct. So
exposed. So
yeah,
the same way only it works, no?
right, same way. What we need to notice is this is basically again your something like your hard disk, right, which contains
Mhm.
a rotating disk. So
Okay.
whatever operation physically the CD or DVD reader and writer is doing, that will be done by
Mhm.
the physical drives. So that physical drives configuration or the working mechanism will be same
Okay. Okay. Okay.
as our hard disk in our system or laptop. So the same work only it
Okay.
will be doing. So
Okay.
to understand how to break down how how it works, how Teradata is reading and writing data.
Mhm.
So that's why we want to understand these indexes, those kind of things.
Okay. Okay.
So this is just to understand how things are done. So mostly we won't be having any control on the drive parts. Okay.
Okay. Okay.
Yeah. Okay.
Okay.
Yeah. So all right. So when an app wants to retrieve a data, so first it will first the table name will be hashed into a table ID, and the app then uses this master index. So this master index will have all the table IDs and which cylinder index that has. So again, what will happen? App will go to the cylinder index and see like which block exactly the row is stored. So we'll be seeing about this master index and cylinder index in detail.
Okay. Okay.
So cylinders again are broken down into permanent table cylinders or spool cylinders. So as we know,
Okay.
spool is a unused space in the disk. Okay, so it is used to load local or temporary data used in the operation. Okay, so
Okay.
once
Okay.
this,
Here also one thing I
yes,
would ask is something like okay, permanent table cylinder and spool cylinder you're saying, right?
correct,
Um, in what the Teradata says, like the unused perm space is the spool space they call it. Okay.
correct, yes.
Okay. In that case, the spool uses RAM kind of a memory, or how exactly, or it is using a physical memory only. So I
Uh,
have that
Okay,
question.
okay. If you see in Windows, right, we have a mechanism called paging. Okay, so
Okay.
what will happen whenever your memory is full, it's almost used, right? So what the Windows will do, it will
Uh-huh.
store the data in the hard drive rather than memory. Okay, so
Okay. Okay.
that is called paging. So it holds some data in the hard drive, and whenever required, right? So
Mm-hmm.
most inactive data it will be stored in the hard drive. So when needed, it will just load into the memory. And then like other inactive data will be written to hard drive. So in this case, like, so the memory won't be 100% utilized, and also it can load bigger amount of data. It can work with your, so similar way. So Teradata has this. Okay, let me show you here. So this is representation how inside that this the things are. So if we see here, that we know that this contains the cylinders and data blocks, right? So this is an example like how the rows are written inside that data block. So these blocks, these are permanent cylinders, and also we have we are divided that space into permanent and spool. So in spool, right, whatever temporary rows, suppose if these rows are selected and it is getting joined, so in that case it will be stored in the spool cylinders. Okay, and it will be purged and then loading back. So it's used as like a paging only when we compare.
Okay. But that is also the hardware only, right?
Hard drive only, yeah.
Hard drive only.
It's stored in the disk only, not in the memory.
Okay. But here that logically it will partition the spool cylinder and permanent cylinder, because if we say like perm space is increasing, then spool will reduce, no? So in that case, that logically it will bifurcate. If we again drop some database or something, that will add that content to the spool like that, or it is already.
Yeah. So we saw in our earlier case, right? Like, so 40% of DBC space should be allocated for a spool, or should be kept empty for spool usage, right? So in that case, when you consider the whole drive, okay, when you consider consider 100, suppose you have 100 TB of space, okay, max space, and you consume 50 TB. So the remaining 50 TB is free in the drive, basically, right?
Okay.
So those 50 TB will be used as the spool space, not the exact 50, but whatever needed, it can easily take.
Okay. Say if you are consuming 40, okay, if you are consuming 40, whether shall we, in that case, we'll get 60 spool?
Yeah, we use that spool randomly, okay, not exactly all the 60.
Yeah, correct. But my question is something like, say in 100, okay, just leave about the system related tables and these things. Whatever the space which is left out with the DBC, in that one, this perm space and spool space will come into picture, correct?
Correct, yes.
Okay, so, say we have 100 terabyte of a DBC space. In that one, we have taken some 30 GB for permanent space. In that case, 70 will that 70 GB will be occupied if it is required for spool, or it is restricted to 50 only?
Okay, so in this case, when you have this 30 GB, right? So whenever you do a manipulation of data things, so it won't cross the permanent space. So it will be lesser than that one, because you're not going to read all the 30 GB of space at a time, right? So you will be selecting some rows.
Correct. We are not using, but many users are running the queries, or something our system is busy like that.
Yes.
So what my question is something like that flexibility is there, or it is prefixed? My spool is prefixed component. I just want to check that.
Yeah, it's not prefixed. So whatever remaining space available in the disk, it will be using for this operation, for the spool.
Okay. Yeah, because there is a separate cylinders, no, permanent cylinder and spool cylinder. That's what I was thinking. Teradata has made that bifurcation, or they already they already given that prefixed amount of spool cylinders we have to
Okay.
utilize like that.
Okay. So nothing like that. Nothing is prefixed in the architecture level. So this is just for our understanding how things.
Okay.
Yeah.
Okay, fine. Yeah. Okay, I got it. Okay.
Okay. So if you see this condition, right? Like once the cylinder contains the rows from a permanent table, then that cylinder cannot be used for spool.
Oh, okay.
So spool cylinders, in other words, are unused permanent cylinders.
Okay.
So in a nutshell, like we assign the disk space only to DBC, correct? So in that disk space,
Correct.
if we have 40% free, that will be used for these spool activities. So that's the overall concept.
Okay. Yeah, here they're selling. Okay, correct. In the next sentence, it is there. Yeah, unused permanent
Yes.
cylinders. Okay.
Yeah.
Spool cylinders are other words. Unused. Okay, fine. Yeah, now I got. Okay.
So we'll be seeing about this full cylinder read. So Teradata is able to read a full cylinder. So at a time. So that is called a full cylinder read. So the full cylinder read allows for all the blocks in that entire cylinder. So cylinder will contain several blocks, right? So Teradata can read the entire all the blocks in a cylinder in a single IO operation. Like when that particular cylinder is read, it can load everything into the memory. Like all the blocks can be read at a time. So the best queries, right, that can take advantage of full cylinder read or full table scan when the data when the operation is when the P is doing a full table scan. We saw earlier, right? Like all the rows, each and every rows are read in the case of full table scan. So basically, all the cylinders are read, right? And when we go in turn, all the blocks are read. So when one cylinder is read, all the blocks can be read at a time. So these full cylinder read are mainly used for these aggregations, large table selects, merge insert, merge select, merge delete, inner joins and outer joins. So instead of reading block by block, it can read by cylinder. So the operation will be faster. So again, this full cylinder read is not always on or automatic by default, but it has to be set by the Teradata support team when we are configuring the machine initially. So there will be a flag for this, so we need to set that to be on in the parameter, DBC parameters.
Okay. If they're taking the advantage of the full cylinder read, means it will help in the performance on the performance side.
Yes.
Or how?
Yes. So sometimes it helps. Okay, if your data is somewhat moderate, it will help you. But when you have very huge number of rows, a very big table like 2 TB, 3 TB of table, when a full table scan is going, it's not recommended.
Okay.
So that comes under full table scan. So here we are seeing about the full cylinder read only. Like whenever there is full table scan, this operation will happen.
Okay.
So the next thing is table header. So whenever a table is created, the first thing the database does is to create a table header on each channel. So this is like creating what to say, like, even though if we don't load the
It is
records.
something like one, we call it as like the schema, whatever is there, like that one pattern kind of, or we can container kind of thing.
We can consider
it will,
this. Yeah, you see here, you see this example. So we have this
yeah.
order table, right? So for this order table, in each
Yeah.
AMP, order table header will be created.
But again, we can just draw lines also. No, if it is 20 columns, means something like we can draw a line, right? Row level it will store, correct?
Yes. So first, right, initially, whenever you create a
Oh, sorry.
table.
Okay, yeah, I got it. Okay. Yeah, this table header means just to get that connectivity, that header will be there. Okay, sorry.
Right.
Okay, yeah,
Right.
I think that is different. That is
That's,
different. Okay,
yeah.
storing
So
data. Okay,
yeah.
just
So,
it is a pointer. It's a kind of a pointer, or it will something for a table recognition. It is table header will be created in all AMPs, correct?
okay. Yeah. We'll see like what is in the table header. Okay. So.
Okay.
So this table header, right? So it contains the column names and the data types and their compression information. So this will be stored in the table header. Okay.
Okay.
So if your table header is corrupted in any of the AMP, okay, then the data won't be able to be retrieved. You won't be able to retrieve any data from any apps. Okay.
Okay.
So this kind of things happen during migration, like when you do a migration from, when you upgrade to higher version. So in that case, there is a chance of a table getting corrected. So in that case, we can't do anything. We need to drop the table and then we need to restore it. Okay. So
Okay. Store it
yeah.
from the tape backup. You mean to say?
Yes, from the tape backup.
Okay.
So even though no rows have been added to the table, right? So the table header will be present in all the apps whenever you create it. So when the rows are added, so it will create the data blocks to store the rows.
Okay.
So in a physical world, table header is separate and the data blocks are separate. But logically, if you see, we can consider table and then header in the same.
Okay.
So, and also if a compression is used, right, on a column, so that value will be stored in this table header.
Okay.
And the actual data rows, right, so that will be flipped in the header like 0 and 1. So that that data will be representing like the detail of values which is stored in the blocks. Okay, so this thing will be seeing detailed and we see about the compression, how the compression works.
Okay.
So just to let you know, the table header contains the details about the column names, the data types, and compression details.
Okay. That means the table header will be containing the metadata information, correct?
Correct. Metadata information about the table.
Okay.
So the next one is the table ID. Okay. So Teradata tracks every object by giving a table ID whenever the object is created. So this comes from the data dictionary table called dbc.next. So this dbc.next will have the metadata about what is the table ID, what ID has to be given next. Okay. So the dbc.next table is assigned to increment by 1, providing the Teradata objects. It means like whenever a new object is created, it will be incremented by 1. That table. Okay. So when you write SQL, accessing the particular table, then Teradata converts the table name to its associated table ID.
Okay.
And
for Teradata, name doesn't matter. Matters is ID only.
ID, right? Yes.
In its architecture for humans or the one we are using the application, we are giving the names, but for Teradata that is ID, table ID it is storing.
Table ID, correct, exactly.
Okay.
So this table ID, right? So this includes databases, users, tables, rows, profiles, views, macros, procedures, index, everything. So whatever object is created, it will be given a table ID.
Okay.
So, and each column and index within a table, right? So that is again given a numeric ID within its table ID. So we'll see what that is. Like a table ID is a 48-bit number, okay? And it consists of two major components. The first one is the value from the dbc.next. So this portion will let the will let the Teradata know, like if the table is a permanent or spool table or permanent journal table. So those kind of details will be present in this first set of 48-bit. Okay, and then the second part of the table ID, right? The 16-bit. So it will tell whether the data row it's primary data row, fallback, or secondary index block. So those details will be given by the second part. So the table ID with the row ID combined will give the Teradata the unique value for each row. So if you see here, so this is the table ID. Okay, 48-bit table ID.
Okay.
First 32-bit from bbc.next, it will give permanent tables, full table, this kind of what kind of table this is. Okay, and then the next 16-bit will be describing about the block. Okay, the primary data rows, fallback, or second index, those kind of details.
Oh, okay.
Okay, so
can you just go to that slide here?
Yes.
Here the row. Okay, here this is fine. Okay, primary data rows, fallback data rows, secondary index data rows, but table header. Why there 16-bit number describing the okay.
No,
there is no.
No, again, see if you see the earlier topic, right? This table header again contains the sub details about the columns, data types, those kind of details, right? So, so this 16-bit, right? It will have details about this table header, primary data row, whether it is fallback, those kind of details will be stored here, along with the table header.
Okay. Okay, fine. Okay, got it.
So for each table, we'll be having a table header, correct? So
correct, yeah.
So so with this 48-bit, Teradata will know like what is this table and what are the columns in this table. Those kind of
sorry, I confused between table ID and table header. Okay, now I got the catch. Okay. Because different things are there now. So
correct, yeah.
Table ID have bifurcation of 32-bit and 16-bit. In that one, first 32-bit will say like what kind of a table. Next 16-bit will say like the table header and the blocks linking with that one. Okay.
Yes.
Yeah, I got it. Okay. Okay, you can continue with the next slide.
Okay, So so the next thing we'll be seeing about is the data block. So once a table has been created, we know like a table header is created on each app. Okay, and the table header basically contains the column and the data type details. So when a data row to be loaded or inserted. So each AMP, what it will do, it will allocate at least 512 bytes of sector inside the disk cylinder. Okay. And this 512 byte sector is considered a block of data. Okay, so this 512 byte of sector will be on all the cylinders from all the AMP. Okay.
No, 512 byte sector. Okay, that is in one place, correct?
Sorry, can you come again?
No, you are saying amps and all, right?
Yeah.
Why, what? At least 512 byte sector, you are saying that with respect to 1 amp, correct?
Yes, this 512, yes, that's what each amp will allocate 512 bytes. So whatever amp
okay. When
is
data
involved, like all will all will allocate 512 bytes.
Okay, inside data. Okay, fine. Okay,
yeah.
That means whenever we started writing data, it will create a space of 512 byte
Yes.
to store that row in all the amps and what are all the linking disk cylinders. Okay.
Right.
I
So,
got it.
yeah, so initially it will be a 512 byte. So if we see here, as we load more and more rows are added. So when the first 512 byte is filled, right? So app will again allocate another 512 byte sector.
Okay.
Okay. Now these two sectors with the size of 1024 byte, and this is considered one block of data now. So earlier we had 512. Once that is filled, it added by another 512. Then this is considered a block of data. So what will happen? Teradata will continue to add sectors until it reaches that max block size. So we'll set up this max block size when initial setting up the system. Okay. So when that is reached, suppose we have you tell like 2 MB is the max block size. So in that case, so until 2 MB is reached, it will be added. The sectors will be added for the block.
Okay.
You got that, right? So initially it starts with lesser amount of 512 byte, and then once that is filled, again 512 will be added to the data block. So once that is done, another 512 will be done. So that will go on until the maximum capacity of block size. Okay. Yeah. So if this block.
No, here they will call it. Okay. Here one sector. Here next diagram 2 sectors. Next diagram 3 sectors are there, right?
Yes.
Are we considering this one box as a block, or here 2 are there? The 2 combining together we call it as a block.
Yeah.
Or next one we have a 3. That 3 also combined together we call it as one block, or how exactly?
Yes. So initially it started at 512. We consider that as a block. So sectors are being added. Then these two sectors will be a block now. Okay. So you see here the 2 sectors now contain 1024 byte, and this is still considered one block of data.
As one block of data. Okay.
Yes.
This sector.
Okay. So when the max level is reached, then block split will happen, which means the next block will be started writing. So it will again start from like this. Okay.
That means it is keep adding sectors. When maximum size is reached, then that block will split and new block will be started.
Yeah. Right. Exactly. Yeah.
Okay.
So this is a good design, because in most of the databases you will be assigning allocating space for the table. If you see in Oracle, if you have worked in Oracle, I think you need to specify a space for a table, right? So mostly, DBAs need to calculate the space, and then they need to do the space management, because there will be thousands of tables, and we can't be doing it for all, right? But in Teradata, it's all automated, so we need not to worry about the block size and those kind of things. So it will automatically.
Okay, in Oracle, DBA has to give that much space, and then it will go like that.
Yeah, I think they need to specify the space in FreeF for
Okay.
for storing the data in the table.
Okay, if something it is going out of what they have assigned,
then
in that case,
you will get a error message like space is full or something like that. I know.
okay.
Yeah.
In that case, they should add additional space.
Correct.
Okay.
Correct.
Okay.
Might be now they might have changed that, but this was initially the thing.
Yeah. Okay.
So yeah. So this block size, right? So we need to decide and set the maximum depending on our workload for system. So tables which are accessed most of the time by a full table scan or should have a big data block size. So so in that case, a block will be read at the time to save the time.
Okay.
Got it, right?
Yeah.
This is about the data blocks. And so this is an example of a data block. So again, the cylinder holds these sectors, one or two or more sectors will make up a block of data. So rows are held inside these blocks. Those are stored inside this block. So when the max is reached, it will be split into the other blocks. So this thing is called a block.
Okay.
So,
Okay.
yeah.
Can you just read that below lines? So cylinder hold disk sectors.
Yeah. So cylinders hold these sectors. Okay. So this is a cylinder. As we saw earlier, this is a cylinder in a disk, and inside the cylinder are the sectors, right? And inside the sectors are the rows, actual rows.
Okay.
Okay. So one or more sectors here, like we have two sectors here, you see. Okay. These two sectors form a data block. This whole thing is called a data block.
Okay.
So initially, this data block will be of 512 byte. Sorry, this sector will be 512 byte and added 512 byte, and then it will add 512 byte. So this will be a data block until it reaches the maximum size.
Okay.
Yeah. So a table might consist of several data blocks, right? But that data block will not be shared with multiple tables. Okay. So one particular data block will be used by only one table.
Yeah. They followed something like shared nothing architecture, no? Teradata.
Yeah. So that is for the shared nothing architecture is for physical entities like your RAM, CPU, or disk drive, those kind of things. So when it comes to this storage part, right? So so this data block, suppose consider this example, we have this data block, right? So this data block will be allocated only for this table, order table.
Okay.
So in case you have no order table backup or order table info, any other table. So in that case, separate data block will be allocated for it. So it won't share the data.
If you are creating some sales kind of information and a purchaser or supplier kind of information, if you are created, means those tables won't fill the or won't get the space of the order table header blocks, right? Then they should have a they should, for them, each separate block is created.
Correct. Yes.
Okay. Okay.
So, and then when we insert data into a table, okay, so what will happen? The rows are placed in a row ID manner. If you see here, if you see in the below example, okay, so the rows are sorted with the row ID.
Okay.
So when inserts add a row, then to a table, then row is added to the end of the data block. So if we add a new row called row 11, it will be added at the end, because this is already sorted out. Okay, so if you see here,
this is that row ID, the same with that hashing value generates 32 bits and uniqueness value, that one only, right?
Yeah.
32 bits of the something and plus again 32 bits something will be there. That is, we call it as a row ID.
Row ID, yeah. So uniqueness value plus the hash value, that is called the row ID.
Okay.
Yeah. So this is how the rows are stored. Like it's sorted and stored. So whenever a new rows comes, it will be loaded at the end of the data block. Okay. And then the row reference array is always sorted by row ID, okay, in descending order, and it points to the exact location of the row, which means this array we see here, right, the down. So it will have like which row is stored where inside this data block.
Okay.
So what will happen when the system searches for one row? So it will come here, it will search, it will do a binary search. So binary search is nothing but like it will go for some random rows. Okay, it will go suppose for row 4, it will see and it will check, is that a row I'm checking? If not, it will go again for the other rows. So that is called a binary search. So this helps in faster speed.
Okay.
Great speed. So basically, this data block contains the rows as we saw here. Next thing.
Okay. Something they call it as a binary sort, that it will follow that algorithm, correct?
Yes. So whenever
there is something different algorithms are there, no, bubble sort, binary sort,
so
and one more sorting mechanism is there. So it will follow, I think, binary sort.
Yeah, binary sort might be. I'm not sure about the sort, but it's called as a binary search. So it will do a random.
Okay, no issue. Okay.
Yeah.
Okay. Binary search. Okay, fine.
So this is how a row is found by the system. So so the Teradata accesses the data rows quickly by utilizing the master index, and then with the master index it finds which cylinder the row is stored. Okay, and then it uses the cylinder index to find which data block it is stored. And then it goes inside the data block, and then via binary search, it finds the exact row.
Okay.
Even if needed, it reach the entire block within the cylinder.
Okay.
So this is the flow actually. Yeah. So master index, then cylinder index, and then the data block, and within the data block, a binary search will happen for a row.
Okay, 1 minute. Let me. Okay, can you just read this below this one? PE comes up with the
Yeah,
plan,
so
sends
this
a
is,
message.
yeah, so the PE comes with a plan and sends a message to AMP via the message passing layer containing, okay, table ID, row hash value, and primary index value.
Okay.
Okay, so the AMP no access its master index. So this master index is stored in each AMP as we saw earlier, right?
Okay.
So with that help, it will find out the cylinder, and then the AMP will access its cylinder index, and then it will find which data block it is. And then the AMP searches the data block with the binary search in order to locate the row.
Okay. Okay, fine. Okay, I got it. Okay.
Yeah.
Okay, the master index is always memory resident. The cylinder index and data blocks are accessed via AMP's FSG cache.
Yes. So whenever the system boots, right, this master index will be loaded into the memory.
Okay.
And this cylinder index and data blocks are stored in the cache memory.
Oh, okay, caching mechanic. Okay. Okay, that is not a permanent. Okay, that is
yes, because
it has to load it to the cache memory whenever the system starts. Correct?
Because this keep on changing, right? Whenever you insert rows, when you do
correct.
insert, it keeps on changing. So it is kept in the cache.
Okay. And if you are using cache mechanism, means that that also works faster, no? That cache memory.
Yes.
Searching and these things. So that will improve the performance. So
correct. Yes.
That is that cache works faster than a RAM, right? I think.
Yes.
Correct. Okay. FSG cache. Okay. Yeah.
This is how a row is fetched. Okay, so let's see about this master index and cylinder index in detail. Okay, so as we know, each AMP has a master index, and that will be in alphabetical order. Okay, so it will be in a sorting order. Okay, so the master index knows the table ID. And it has detail of what is the lowest row ID and the highest row ID. Okay, of that for that table. Okay, if you see this example here, so it's sorted out with the table IDs. 1, 2. These are table IDs. Okay. And then if you see here the row IDs, right? So you see it is also sorted. So it knows like which is the for table 1, which is the lowest row. So this row ID is the lowest row for this table. And for this same table, the highest row hash is this value, right?
Okay.
And that is stored in cylinder 10. Okay. So what P will do when it comes to this master index, it will look for this table ID, right? And then it will see which row. It knows the row ID, right? So it will see if the row ID is between this range. Okay. If it is in this range, it will directly go to the cylinder.
Okay, say we have created some 1,000 table, means we will have 1,000 IDs, right?
Yes.
Specific each table.
Yes. So whatever tables involves the AMP, so it will have all the details.
Okay. And it will be having the information of lowest row ID value and the highest one.
Highest value. So when the data comes between this, so it can easily identify. So this is in this cylinder. Likewise.
Okay, it will go to that cylinder and pick that one. Again, in the cylinder index will be there.
Correct.
Okay.
Yeah, I will be seeing that about the cylinder.
Okay, fine. Yeah.
Okay, so we'll see about the cylinder index. Okay, so each amp again has a cylinder index that is organized in alphabetical order, the same as the master index. So mostly this cylinder index and master index are same.
Master index,
yeah.
that master index available at which level? AMP level?
Yes, amp level.
Okay.
So if you see here, each amp has a master index.
Master index. Okay.
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 Yeah. So this cylinder index, right? So again, it contains the detail about like the rows, like which blocks it is stored. If you see this example, yeah. If you see this example, you can see like yeah. You see this, it contains the lowest row ID and highest row ID again. And then it has the sector details.
Okay.
Okay. So the starting sector is 20. So those kind of sector details it will be having the block details.
Okay.
So
there is okay. DPA need not to in the sense like not to bother about this these things, right? In the physical world.
No, not even. Yeah.
Okay.
So this is for our understanding, like how the data is stored.
Okay. Well, can you just go to the previous two slides?
Yeah.
I think you are just explaining. Previous to this one, one more slide was the one.
Okay.
Yeah. I think here you are saying.
Yes. So the cylinder index, it has the table ID and it has the lowest row ID and the highest row ID again. And this allows the AMP to scan the cylinder index to exactly locate the data block.
Okay.
And from the data block, it can read the rows inside it.
Okay.
So,
okay, this might now, okay, I'm just reading the second line. This might now give you better understanding as why AMP keeps its table separate data blocks and why it sorts those data blocks by row.
This is for achieving the fastest speed. Why it is not combined with other tables. So each table has its separate data blocks, right? So in that case, whatever related to the table will be read fastly instead of filtering out for the other tables. So that's why the data kept it in this way. Separate data blocks for separate tables. So again, each cylinder index, right? So it used to build the master index, right? And whenever a system boots up, and when you reboot the system, and this has to be reboot.
Okay.
Yeah. So because we saw like cylinder index will be the master index will be in the memory and cylinder index will be in the cache.
Okay, master index will be on the AMP level, cylinder index will be on the cache.
Correct, yeah.
Or it will be
it even both master and cylinder are AMP level only, but only difference is this master index will be loaded in the memory and cylinder index will be loaded in the FSC cache.
Oh, okay. Okay.
So if you see again here, each AMP has a cylinder index. Earlier we saw each AMP has a master index, right?
Correct. Yeah.
Each has a cylinder index. So it's on AMP level only, but where it is getting stored is different. So master index is stored in the memory and cylinder index is stored in the cache.
Okay.
So the combination of this master index and cylinder index allows each AMP to find the proper cylinder data blocks and then the corresponding rows as we saw earlier, right?
Okay.
So you got the overall picture, right? Like how it's stored in the master cylinder data block, then rows.
Yeah. I got it.
So there is a functionality called the defrag. Okay, so what the
Uh-huh.
Teradata do is it collects the free blocks whenever the system is not busy. Okay, so
Mhm.
it will collect the no, details about the blocks, like how many sectors are used, how many is free in the
Mhm.
block. Okay, and this collection is called defrag. Okay, so why this is done is like whenever a new row is inserted, so the block it will be added at the end of the block we saw, right? So it will be easy
Okay.
to store it on at the end. Okay, if you see this example, okay, this is where before defragmentation is done. Like if you see here 5 sector block is there, that two is unused sectors, and then there is another one unused sector inside this block. Okay. So after defrag, what will happen? All these unused sector will be moved down, and then
Mhm.
it will have 3 unused sectors. So whenever a new data comes in, this it will be loaded into these sectors.
Okay.
Okay. Um, yeah. So both blocks have enough room. So this is another example. So if you see here, this first example, we have a space where the data can be written, right? So there won't be any problem in loading the data here because this is the last row, correct? So
Okay.
this is in this case the fragmentation is not required. So, but when we consider this example, okay, there is row
Mhm.
one, row two, but still there is some space in the sector. Correct.
Correct.
So
Yeah.
what will happen? The defrag will be running and it will be moving the data,
Yes.
means the space at the end, and it will be adding the new row.
Okay.
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 Okay. So we'll see about no, what will happen when there is a full cylinder condition. When the cylinder is
Okay.
full. Okay.
Okay.
So the cylinder full condition happens when there is no block or free block, no, that is enough to hold the data. Correct. So
Okay.
Teradata does a four steps to fix this condition. Okay, the first one is
Mhm.
defragmentation. So that is what we
Mhm.
saw, like collect all free blocks in the cylinder
Mhm.
and then move them to the bottom of the cylinder by moving all the data blocks towards the upper. So basically defrag. Okay,
Mhm.
and then the cylinder migrate. So what will happen? It will check the logically adjacent cylinders to the left and right. Okay, and then if room is there, then it will move 10 data blocks to the adjacent cylinders. So this is called
Okay.
cylinder migrate.
Okay.
Okay, and then cylinder split is like it checks for the free cylinder and then moves maximum 20 of data blocks to newly, like it will create a new cylinder. Basically, that's what it means. Another cylinder. Okay.
Okay.
So here it migrates to the existing cylinder, the cylinder migrate. And the cylinder split, it will split into a new cylinder and it will start writing. It will move some space, some existing data blocks to the, so maximum of 20 data blocks, which is existing here, the old cylinder, it will be moving to the newly splitted cylinder.
Okay.
Okay. And there is something called mini cycle pack. So so this mini cycle pack will do free up on the cylinders. So how this is done is like moving the data blocks to the top again to free up the space at the bottom. If you see this example here. Okay, so if you see here the cylinders, we have data blocks, right? So
Mhm.
if you see, we have little space in each block. So what it
Mhm.
will be doing, it will move all the data blocks inside the cylinder up toward the top, and it will free some space here. So that this cylinder can be used again for
Okay,
data
okay.
storing.
Now this is something. Okay, okay. This is something happening at a cylinder level. Okay.
Cylinder level, yes.
Oh, okay, okay. Okay, okay. Defragmentation, where it will happen. This will where it happen. I'm just thinking. Oh,
This
block level.
defrag will be on block level. Okay,
Okay,
the
okay.
concept is similar, but when
Hmm.
it comes to cylinder, we have this thing. So both in block
Okay,
level,
okay,
also in cylinder level, this happens to free up the space.
okay, okay. Yeah.